Within recent months, the Atomic Energy Commission and the Department of Defense have conducted important tests of an experimental device based on the thermonuclear principle, leading to the development of a very large yield weapon. In addition, a proof test was made of a large yield fission weapon. These constituted Operation Ivy. The report of these accomplishments is about to be presented in film form. We will show you new techniques and new scientific developments. We will minimize the portrayal of normal military service support, since you're familiar with this aspect of test operations. As commander of Joint Task Force 132, I invite you to observe Operation Ivy, carried out on our Pacific Proving Ground, Aniwetok Atoll.
No. Where I feel right now, I just moved back to Pearl.
You may be right. I hear this is going to be a big one.
You aren't kidding. We wouldn't be out here in open sea if it wasn't a big one.
Captain, we're in position. Recommend reduced speed, sir.
Very well, Mr. Adams. Helmsman, steady as you go.
Steady as you go, sir.
All engines ahead 1/3.
All engines ahead 1/3, sir. Engine room con ahead 1/3. All engines answer ahead 1/3, sir. Engine room reports making turns for 4 knots, sir.
Very well. How are the wind and tide affecting us?
As predicted, sir.
Good. It's important that we stay within that area so we remain within the television cone.
Yes, sir.
Welcome aboard the USS Estes. As you may or may not know, the Estes here is the command ship of Joint Task Force 132. We have minutes to go before the first blast, mic shot, of Operation Ivy. 59 minutes now, to be exact. We've been here since daybreak. Left Wetok last night during the early morning hours. Now, as you can imagine, feeling is running pretty high about now, and there's reason for it. If everything goes according to plan, we'll soon see the largest explosion ever set off on the face of the Earth. That is, the largest that we know of. Some 8,000 men will view the event from this point. Oh, by the way, the carrier over there is the Rendova. She's primarily set up as a base for fighter security and helicopter reentry. And that's the Curtis over here, the weapons assembly ship. In the time between now and HR, I'd like to show you around, if I may, and introduce you to some of the people connected with this operation, and in general, piece together the events which have brought us to this point. To start off, I'd like to show you something over here. You realize there are many miles of ocean between us and Aniwetok Atoll. To know what's going on back at the atoll, these antennas are receiving televised signals and are giving our men here a second-by-second account of what's happening on Shot Island. The television receivers are in here, in the control room. Oh, but before going inside, let's take a look at a chart. It may give you a better idea of our location. This is our position. 10 miles south of Enuitak Island, or about 30 miles south of Ugalad, the Shot Island. We must keep a very accurate position here because of the televised signal. It's a very narrow beam, and the ship must stay within that beam. Now, perhaps you're wondering why we're out here in ships. Well, the answer is very simple. It's too dangerous on land. We're expecting a yield of from 4,000 to 10,000 kilotons. That's equal to between 4 and 10 million tons of high explosives. Considering all possible effects from a bang of this size, the best observation point is at sea, on a mobile platform at a known safe distance from 0 point. Okay, let's go inside now. Well, this is it. This is the control room. I'd like to have you meet Mr. Stan Burris, the commander of the scientific task group. Oh, Stan, I wonder if you could tell us something about the operations that go on in this room.
Sure, I'd be glad to. The screens you see in front of you enable us to monitor the timing and firing system and the cryogenic system. The lights indicate that the timing signals are functioning properly. The dials, this collection of dials, indicates that the liquid deuterium is in the proper state for firing. If you will look close, you will see that it is now 55 minutes before H hour. As time clicks off, more and more lights come into operation. This is the 1 minute light, 30 second, 15, 5, 1 through firing. Since this is a thermonuclear test, we are using a type of hydrogen in a liquid state. It is necessary to keep a close check on the condition of this fuel. If the hydrogen is not in the proper state or at the proper level, it would have such a marked effect on the results that there is no point in continuing the experiment, in which case we would postpone the shot. Is there any chance of that so far, Bob?
No, there isn't, Stan. The cryogenic system has been operating perfectly for several days, and we're not particularly worried now.
That's fine. I have here a layout you may be interested in. This diagram will give you a general idea of the whole setup. Data from the sequence timer is piped over to a display panel. Likewise, cryogenics data is piped over to this display panel. This kind of display panel is new to atomic test work because of the large number of remote control and metering problems encountered in this operation. For one thing, the master timing and metering apparatus is located next door to the shot cab, rather than being placed some 20 miles away on Parry Island as is usually done. This close view is possible, of course, because the lens of a television camera, rather than human eyes, is watching events. So cryogenics data piped direct from Mike and information from the sequence timer is transmitted from the small building attached to the main cab and is relayed by way of a TV antenna atop a 375-foot tower to the Estes.
So that's the flow. From timer on through to display panel, cryogenics data to panel, picked up by a television camera and relayed on out to the Estes. A very ingenious arrangement. But what happens if you have to stop the firing mechanism, or can you stop it?
We can stop it all right if we have to. We have a radio link direct to the firing panel in the shot cab. If we have to stop the shot, we simply push this button.
Just a simple flip of the wrist, huh?
That's right, but a lot of work goes down the drain. You understand we don't want to stop this thing unless it's absolutely essential.
No, I can understand that. Say, I was out on deck when you fellas returned. Well, that is, when the firing party returned. What happened out there on Shot Island?
If you'll excuse me, I suggest you talk to Colonel Lunger about that. I have a timing signal coming up.
All right. So then, Dick, the firing party's big job is to see to last-minute details of arming and firing and to make sure that the Shot Island is secure.
That's the broad brush of it, yes.
I've been a member of firing parties before, but this was different somehow. A man standing, as I stood, on the outside of the building housing the mic device couldn't help but feel, to sense the importance of this moment. Inside, a handful of men were making a final check. Were arming a device which could be the key to a new era in atomic weaponeering. I don't know just how the others felt, but I felt small when I thought of the experiment being readied inside. This one test could take us out of the realm of kilotons into the fantastic world of megatons. And then, at H-6 hours, the job was finished. The mic device was on its own and ready. We all moved to take a final look at the gadget, which represents a year of intensive engineering. As we moved toward the pier, one couldn't get away from the feeling of being alone, of knowing you were the last to leave an island which might be shocked beyond human re-entry. We made the run from Shot Island down to the anchorage of the Estes off Perry in a fast crash boat. Soon after, the Estes made way through the deep entrance between Perry and Japtan Islands, out to a point 10 miles southeast of Perry, the rendezvous area of the task force ships.
We finished our job at the cab, came over the side, and here we are. Waiting on station just like everyone else.
Well, we won't have to wait much longer, Dick.
All right, thanks.
Well, that's part of the story. A small part, actually, of this whole ball of wax. An operation like Ivy has many facets, some large, some small. Behind the present activities on this ship, behind what went on at the atoll itself, whatever preparations had to be made in the States, is the broader story of policy, philosophy, of planning. Now, this deeper story, the background, so to speak, has its roots entwined in the broad international picture, in the larger aspects of the atomic weapons development program, in complex scientific conclusions. Not long ago at Los Alamos, I was talking to Dr. Alvin C. Graves, head of the test division there. He's on board now in Flag Plot as the scientific deputy to the task force commander. He's one of the men who can tell us about the thinking behind this operation.
And we're not really sure of what progress the Russians have made in this business of nuclear research. And so the only safe assumption to make is that they're interested in producing a fission bomb and to use it as some sort of trigger mechanism for a hydrogen bomb. It's obvious we don't want them to have a hydrogen bomb before we do. And so time is urgent. Time is the thing we have to beat.
Dr. Graves, the historical side of this operation is particularly important. I wonder if you'd mind speaking right to our camera.
Not at all. First, let's go over this business of the hydrogen bomb. Why use hydrogen? Hydrogen permits us to have an inexhaustible source of energy. It's plentiful. We don't have to worry about the critical mass limitation. Second, we can get hydrogen very cheaply. If we can use deuterium, we can distill it from ordinary seawater. We're floating on it right now.
That's very interesting, Doctor. But what is deuterium?
I was coming to that. First, let's consider ordinary hydrogen, such as is used commercially. An atom of this kind of hydrogen has the simplest nucleus known. It has one proton. But hydrogen exists in two other isotopic forms. Deuterium, which has a neutron in addition to the proton, and tritium, which has two neutrons and one proton. Ordinary hydrogen is not considered a good bomb fuel. And tritium, because of its expense and rarity, can only be used in limited quantities. Well, that's part of the background of Ivy leading up to the present.
In 1 minute, it will be H-45 minutes. H-45 minutes.
Stay on deck for a bit.
All right, fine, Doctor.
Beginning to get light.
Quite a bit.
Hi, Jerry. Worried about Mike?
Well, it's too late to worry about that now.
The Shot Island is about over there?
That's right. It's generally north and west of us. For the past half hour, the ship has been headed directly toward the Shot Island, and will continue to do so until shot time.
You know, there's one thing I can't quite put together. That's this business of success or failure. I've heard there's a 50% chance of its failing. Now, this low margin of success wasn't true on the other shots, was it?
No, it wasn't. Let me try out the Admiral's chair.
Sure.
Up until this operation, that is, from about 1945 through 1951, the chance of failure has never been more than about 10%. In Crossroads, Sandstone, and Greenhouse, we had great confidence in the operation succeeding. We recognized a change in philosophy, however, when Dr. Bradbury spoke to a group of us at Los Alamos in 1951.
Gentlemen, up to now, the laboratory has had sufficient time to compile information and revise weapon design before a field test of a weapon. As of now, the situation has changed. We must take risks. Calculated risks, it is true, but risks nevertheless. According to the presidential directive, we must ascertain if a hydrogen bomb is feasible and do this in the highest possible speed. We must ascertain if such a bomb is feasible, if we can, in 1952. Here is what I think we must do. We must set up a special staff under Dr. Marshall Holloway, reporting directly to my office. He will receive from the theoretical division the theoretical designs of such a system, have them fabricated and shipped to Eniwetok. There, they'll be taken by Dr. Graves and J Division and tested. It must be recognized that we're taking great chances, a great gamble, but a gamble, while there's a possibility of failure, nevertheless there's a possibility of great gains. Eniwetok will become our theoretical laboratory rather than a proving ground.
And that's the way it is today. We're taking a gamble.
I see that now. But then the uneasy state of the world puts everything on a gambling basis, I guess.
Yes, but not as much of a gamble as you might think. Take that man over there. He and his company have put a great deal of thought into the engineering and design of Mike. Well, see you later.
So long, Doctor, and thanks a lot. I couldn't help coming back to the control room for another look. They tell me everything's going along without a hitch. I've been taking a closer look at the cryogenic screens there. You know, there's a lot to this low temperature work. In a good many respects, it's the most outstanding problem of the entire operation. And as soon as Bob Gibney can break away, we'll talk about some of these problems. But this I know. A lot of heads have been scratched trying to figure out some way to work with various gases which have to be brought down to a liquid state. Oh, Bob, I've been browsing through this subject of low-temperature physics.
That's quite a subject.
It sure is.
The general problems connected with very low temperature operation had been met on the George shot of Greenhouse. The amount of thermonuclear fuel required for Mike's shot is considerable. Do you remember the buildings in the south end of Perry, near the airstrip?
Yes, I do, Bob.
Well, that's the liquefaction plant. The original plant was established during Greenhouse. Because of the difficulties in transporting, the decision was made to produce liquid hydrogen at Eniwetok rather than in the States. But for Ivy, it had to be expanded considerably. The capacity of the original hydrogen plant was doubled for the production of liquid deuterium, and a new plant was built for the production of hydrogen with a capacity 4 times the old Greenhouse model. The small nitrogen plant was expanded 8 times its original size. For Operation Ivy, the Perry Island plant operated continuously for 3 months to produce the necessary low-temperature liquids needed in the experiment. But of course, you don't put a material so difficult to make and so difficult to keep in milk bottles. You use special containers called dewars, which are simply outsized thermos bottles. Months ago, these dewars were made in Massachusetts by the Cambridge Corporation and driven out to Boulder, Colorado for testing. Each dewar is mounted on its own truck with its own refrigeration plant and generator. Against the picturesque background of the Flatiron Range of the Colorado Rockies, these dewars were filled with liquid hydrogen at the cryogenics lab of the National Bureau of Standards. This plant, set in an unpopulated area, is the largest source of liquid hydrogen today, and hydrogen is essential for a practical shakedown test. The climax for these dewars came out here at Eniwetok when they were actually used for the job intended, transport. Since production of thermonuclear fuels might be needed on future tests at Eniwetok, it was thought best to put the liquefaction plant on Perry Island instead of on the shot island, where it probably would be destroyed. But this meant a satisfactory means of transporting liquid hydrogen from Perry to the shot island. This type of exaggerated thermos bottle, mounted on wheels, was the answer. A dewar is constructed to isolate the contents of the dewar from the outside temperature, so no heat can leak in. Contained within the boilerplate outer shell is an inner shell made of stainless steel with a vacuum in between. This is the container which holds the liquid hydrogen. A radiation shield made of copper surrounds the bottom half of the inner shell. There are two bottoms to the radiation shield, and in the space between them, there is room for liquid nitrogen. The purpose of the radiation shield is to provide a barrier to the flow of heat. The heat which does leak in boils away the nitrogen first, thus protecting the liquid hydrogen. But even with all these precautions, another source of heat still occurs in the inner shell. This is mainly due to a special property of hydrogen. The molecules of hydrogen, as a gas, exist mainly in a state called the ortho. At first, when the gas is liquefied, the molecules stay in their original state. However, within a period of some 2 weeks, the molecules rearrange themselves into a state called the para. This is a natural phenomenon which always occurs. In this transfer, heat is given off, actually sufficient heat to boil off 2/3 of the liquid hydrogen. To take care of this excess heat, a special refrigerator has coils located in the inner shell. The refrigeration plant, which supplies these coils, does a remarkable job, for its coolant approaches absolute zero. Absolute zero, that unimaginably cold zone where everything stops. All life, all molecular motion. Minus 459 degrees Fahrenheit. A little above this fantastic figure, hydrogen becomes a liquid at minus 423 degrees Fahrenheit. This is the temperature to be maintained in the dewar. Only 36 degrees away from the bottom. Absolute zero. The helium refrigerant used can affect a temperature sufficiently low to cause the gaseous hydrogen boiling off to return to a liquid state.
Well, I went into more detail on the cryogenics end of this project than I intended.
Well, so far, we've pieced together quite a bit of this operation. I don't believe you've ever had a good look at our key test islands. The test islands for Mike are located at the top, or the northern sector, of Eniwetok Atoll, some 25 miles from Perry and Eniwetok, the two base islands of this atoll proving grounds. There are 3 main islands making up the test site. These are Alujalab, Teeter, and Bogan. Early in the game, these islands were linked together by causeways. The old business of men and machines digging and piling up coral sand. These connecting roads were built to make it easy to get from island to island, and also to act as land platforms for some of the instrumentation. A sizable camp was set up on Teeter. First, it housed construction people, and later served as an advanced base for scientists working on the shot island. In the early months, Alujalab was just another small, naked island of the atoll. But by midsummer, it began to look like the thing it was selected for, a shot island. Actually, the cab, so called because it houses the weapon, is not a cab at all, but a building set flush to the ground. It has all the earmarks of a common workshed, but in reality, it's a laboratory building set on a Pacific atoll.
How do we stand at Kwajalein?
Charlie?
Then they're all on the way except for the 3rd and 4th sampler elements? Right. Are you picking them up on the scopes as they come into the area? Right. Yeah, well, from here in, let us have immediate notification if exact shot positions aren't maintained.
This is Broadway 3.
Yeah, and the helicopters, we expect to order them out in about...
Aerology, which may require you to move some of your units.
This, as you have probably gathered, is joint operations. All atomic test operations in the Pacific so far have been run under a joint task force kind of setup. Operation Ivy is using the same organizational structure as greenhouse. 4 task groups: scientific, Army, Navy, and Air Force. Members of these groups are here now, sifting and coordinating the many details of this joint operation and passing key information topsides to the command level. The Army is...
Broadway 2, 4 Cape Cod has radar contact skunk.
The Army is the executive agent on this operation, just as the Air Force was on Greenhouse and the Navy on Crossroads before that.
Well, Colonel,
Weather, this is J3. Let me have your latest recon plane VHF report, over.
We'll go. Out.
I've been talking about task force organization. Wish you would add something to help clarify this business of executive agent.
Yes, I'll be glad to. First of all, we are organized along very simple, conventional lines. I believe I have a chart which explains it better. The Joint Chiefs of Staff and the Atomic Energy Commission on this level coordinate on the instructions that are to be issued to the task force commander. The Joint Chiefs of Staff control the operation through the executive agent, the Chief of Staff of the Army. The task force commander has operational control of the Air Force, Navy, Army, and scientific task groups. Now, when we were in the United States, the Atomic Energy Commission maintained a control over the scientific personnel at Los Alamos Scientific Laboratory. However, for the operational phase, the Commission appointed General Clarkson as its special representative, and in this way, he controls the entire operation.
I get the picture, Colonel.
Okay, Tincher, you take this one.
What do you feel are the unusual aspects of your operation?
Well, we like to believe that Ivy is a milestone in atomic development. I believe that in many ways, Ivy is another Trinity, the beginning of something, and we hope the beginning of the H-bomb era. You know, it's been exactly this thought that General Clarkson has had in being so insistent that the task force support elements be emphasized. The fact that all of us must support the scientific people who are doing such important work. I would say that this is the keynote of the operation.
Excuse me.
While we're here in joint operations, it's a good time to think for a moment of the work of the military task groups. Take the Army, for example. This support group, commanded by Colonel George E. Burritt, provides a variety of services which make it possible to conduct an atomic test such as Ivy at a proving ground outside the continental limits of the United States. At this point in our story, it's necessary to understand the effort behind the collecting of measurement data. For what good is a test unless we can learn, can profit from the experience? Highly specialized, sometimes costly instruments help scientists bring home this vital data. An outstanding example of such specialization is the use of a helium atmosphere box by the Naval Research Laboratory. The plywood tube, looking like a train of boxcars, runs from the Shot Island across the causeways to a detection station on Bogan, a distance of nearly 2 miles. Inside the box, the helium is contained in 200-foot polyethylene balloons. some 45 balloons being required to fill the plywood tube. The detailed progress of the mic reaction will be studied by utilizing this device. The measurement starts in the mic cab with a collimating shield, a large concrete block designed to stop all radiation which might confuse the issue. The setup is a lot like having peepholes in a fence. DT neutrons from the mic reaction will pass through holes in the concrete wall and react on iron converters to produce gamma rays. These gammas will then be collimated through the long helium tube or column to the detectors. Helium is being used for a good reason. Gammas traveling through normal air will have a difficult time of it because of the relatively large size of an air molecule. Now the helium molecule is much smaller, and the gammas will have a relatively free path in which to travel, and hence will be 1,000 times more intense at the detectors. This experiment is one example of the kind of unique instrumentation needed for learning the secrets of weapon behavior. In addition to the diagnostic kind of measurement, many studies are being run on the effects expected from a high-order detonation. These projects are being conducted jointly by the AEC and the Department of Defense. As always, there are many questions to be answered. Classical routine questions and special pertinent questions pertaining to the hydrogen device mic. For example, what will be the blast pressure on and near the ground? Many instruments, like the Wianco gauge, will measure overpressures at ground level and from 15-foot towers. What will be the blast effects at low altitudes, say up to 300 feet? Mortar shells will label the air with smoke puffs for photographic study of their action. And what about high altitudes? For this, anti-aircraft guns are being used. The bursting shells from these guns will label the air with smoke up to 26,000 feet for a free air pressure measurement. Not only will the ground and air be measured for pressures, but also the water surrounding 0 point. For instance, what will be the motion of the water waves in the lagoon? To get such data, photography will study the movement of these floating targets. And then what about the underwater shock wave in deep water and its effect on underwater ordnance and vessels? This interesting pressure versus time measurement will be obtained by reading pressure gauges which have been attached to the mooring cables of can buoys. Then there are the questions concerning the direction and magnitude of the wind accompanying the shock wave and the afterwind which follows it. The story of heat or thermal radiation needs continued study. The ever-interesting history of neutrons will be recorded. What amounts of external neutrons are present? And what is their energy distribution? Because of the expected size of the shot, the fallout problem is being extensively analyzed. There are questions on the size of the particles, when they got there, and how hot they are. Rafts placed out in the lagoon constitute one method of collecting this information. For a more realistic kind of evidence, a B36 and a B47 will be in the air to find out the effect of blast and heat on delivery aircraft. These heavily instrumented aircraft should bring back a record which will indicate whether delivery techniques need to be changed for very high-yield weapons. Well, you could go on and on about the experimental projects being run on this operation, but in so doing, you run up against the same old problem. Each project is so specialized that it becomes a study in itself. So we have given but an impression of the 60-odd experimental projects being run on Ivy.
Latest word from the control room is that everything's going according to Hoyle.
Is the hydrogen level holding?
Right, just as calculated.
She's holding. She's holding. Isn't that what you're thinking, Crone? It wasn't too long ago, 50 days to be exact, when you stood on the beach and watched Mike arrive in crates. A thing then dismembered, a sleeping giant, a robot taken apart for the long trip across 4,500 miles of lonely ocean. And then it was home. Here in a building more like a laboratory than a workshop, it would be assembled for the last time. As you looked at the mass of crates and boxes, you couldn't help but wonder, could you, whether there would be time to make order out of this chaos. When you remember back, items moved into place like notations in a diary. Yes, for you, Crone, the days of preparation fly in kaleidoscopic fashion across your mind. Days now in the past, just as Mike itself will soon be in the past.
3, 2, 1, hack. H minus 5 minutes. H minus 5 minutes. The shock wave will not arrive for several minutes after 0 time. Keep firm footing until after the wave passes.
Our latest obtained as a wind sounding.
You've been here before, flag plot.
Shows distinctly.
That's General Clarkson, the task force commander, and General Walk, chief of staff. The scientific deputy, Dr. Graves, you've already met. Captain Paul is deputy for naval operations, and General Wise, deputy for the Air Force. As you've gathered, a weather briefing is taking place. I should say another weather briefing. You've probably heard many times before how important the weather picture is in an atomic test operation. Weather can make or break a test shot. That's why you want to know up to the last moment just how you stand with the elements. The problem this time is especially acute because this entire area of the Pacific is subject to radiological fallout. And this area is inhabited by some 20,000 people. Plus, of course, the ships of this task force. That's why the RadSafe officer works hand in glove with the weather officer. Oh, by the way, to help you understand this problem, these weathermen are covering an area larger than the United States with 10 weather aircraft and 11 fixed weather stations. To put it mildly, that's quite a territory to cover. Let's listen in, shall we?
This is a plot of the latest winds received from Inuitak, showing that in the lower levels to 20,000 feet, we have a typical trade situation, followed by southerlies aloft, by westerlies above that, which extend clear up to 85,000 feet. This is just about as good as we can expect. This picture, in addition to the total weather consideration, indicates that all of the weather factors are favorable for our scheduled event. That's all I have, sir.
Any chance of showers?
Not within the next 48 hours over the entire marshals.
How about cloud cover?
A few cumulus move in, but if we go off on schedule, nothing to bother the operation.
Are you satisfied from the radiological standpoint, Commander Maynard?
Yes, sir. The situation is ideal since the entire fallout pattern is to the north of the inhabited islands.
Thank you, gentlemen.
The time is now H minus 2 minutes.
Okay, I'll check with
H
staff.
minus 2 minutes.
One quick question, Dr. Graves.
Well, that'd be quick. We haven't much time.
I see. How soon after the shot will you know how big Mike went at?
We will get rough estimates, like from the bang meter, a few minutes after the shot. See you later.
Right.
Why, sir?
You have a grandstand seat here to one of the most momentous events in the history of science. In less than a minute, you will see the most powerful explosion ever witnessed by human eyes. The blast will come out of the horizon just about there. And this is the significance of the moment. This is the first full-scale test of a hydrogen device. If the reaction goes, we're in the thermonuclear era. For the sake of all of us, and for the sake of our country, I know that you join me in wishing this expedition well.
It is now 30 seconds to 0 time. Put on goggles or turn away. Do not remove goggles or face burst until 10 seconds after the first light.
15 seconds. Minus 10 seconds. 9, 8, 7, 6, 5, 4, 3, 2, 1, T0.
The cloud is still rising. 70,000 feet now, if the last estimate I heard is true. And up there at this moment is about 45,000 are the sampler aircraft.
F-84Gs, manned jet fighters, are being used exclusively on this operation. Experience has proven that manned aircraft are just as efficient and much less costly to put in the air than are drones for sample collecting. Jets were selected because they can operate at high altitude. Since the force of Mike shot has pushed the cloud up to around 100,000 feet, it is necessary to get aircraft up high enough to get reliable samples. Even at that, they're scraping the bottom of the barrel, so to speak. Some 14 F-84Gs are being used at staggered intervals to get a good cross-section of the cloud at different times. The jets, which are based on Kwajalein, also have the speed necessary to make them good sample collecting machines. For the relatively short length of time the pilot is in the area, he gets a good sample per rate of contamination. One of the disadvantages of using jet fighters is their range. To handle this problem, KB-29 tankers, flying gas trucks, are in the air to refuel the jets on the way back from their sampling mission. The jets are also short on over-water navigation aids.
Charlie 1, this is Red Leader. Request steer to Dog 2. Over. Red Leader, this is Charlie 1, steer 310.
A B-29 control aircraft gives the samplers headings and rendezvous points and generally orientates them in this remote region of the Pacific. The control aircraft is fully equipped with radar and communications, and in essence performs all the functions normally thought of as being controlled from a ground air operations center. A B-36 is also in the air as another kind of control ship, like a football coach running the game from the sidelines. A scientific controller watches the formation of the cloud and directs the samplers in for their runs. When a sampler aircraft has obtained its allotment of contamination, it has done its job and returns to Kwaj.
That's part of the air story going on right now. Other aircraft are getting ready to track the cloud and also to collect samples for long-range detection studies. Dr. Graves?
Well?
Yeah. Do you know the yield on Mike yet?
I'm just going to find out now. Come along.
The bang meter records are in. The dots indicate the time in milliseconds.
Well, what's the verdict, Herb?
About 12 megatons, Al.
Nice going.
What this tremendous blast did to the atoll, nobody knows. Re-entry parties are leaving the Rendova now by helicopter. The Navy Task Group, commanded by Rear Admiral Wilkins, has the problem of providing the means to re-enter shortly after the blast, to get exposed film, samples, and other scientific data. Since no land mass is available, the problem is complicated. Re-entry must be from a ship. Further, fallout will be very high, starting at about M+1 hour. Helicopters must get in quickly and get out again before that hour is up. One survey group is leaving here from the Estes. I can't go along, but you can, and see for yourselves, through the eyes of the camera, what has happened back on the atoll.
Approaching ground zero. Coming up on Bogon. The detection station on Bogon appears to be in good shape. No visible sign of plywood tube. All test islands seem to be swept clean. Ugilab is completely gone. Nothing there but water and what appears to be a deep crater. Water dark blue in color.
Well, the Mike phase of Operation Ivy is about over. The next and final phase, King Shot, will be an airdrop of a large yield fission weapon. And for this, I'll leave you to the air.
Destiny Control, leveling out at 8,500 feet for IFI.
The drop aircraft for King, this B36, is on its way to the target point. Steadily, monotonously, it wings its way from Kwajalein to a point in the sky over Eniwetok Atoll. For the first time since Operation Crossroads back in '46, an atomic weapon will be airdropped on our Pacific proving ground.
AC to pilot, will you take over for a while?
And you, Colonel, what are you thinking as you relax for a moment from the controls of this strategic bomber? This bomber whose cockpit now resembles a closed room, curtained off from possible dangerous effects of heat and light. Are you thinking of the mission, or of Kwajalein, or perhaps of home? Home, you certainly can't call Kwajalein home, even though it now looks like an extension of the Carswell Air Force Base. Talk about crowded. In addition to the normal complement of the island, Kwaj has been the major base for our Air Force ever since this operation began. This small atoll island is the jumping-off spot for the air group, commanded by Brigadier General F.E. Glansberg. Operation Ivy isn't like Greenhouse, when Eniwetok Island was used in addition to Kwaj. In a sense, Wetok is still used, but just for L-13s and copters, aircraft easy to evacuate. Look at this lineup on the Kwaj airstrip. Samplers, tankers, weather ships, photo aircraft, trackers, control planes, drop aircraft. Looks like it's harder to find a parking space here than in downtown Fort Worth on Dollar Day. But now Kwaj is behind you, Colonel, and you're on your way to doing something big. Big, like you were told back at the briefing.
So much for the operational plan. Perhaps some of you are wondering about the idea behind the dropping of such a high-yield weapon. General Glansberg has a few words he'd like to say to you on this subject.
The Department of Defense has indicated that certain targets may require a bomb of such yield as the one you will be carrying tomorrow. And it's your job to put it down the pickle barrel so that they can do a decent job of proof testing it. One other thing, there's been a lot of talk about why we selected the B36 to do this job. The reason the B36 was selected is because it has metal control surfaces. There is still some argument as to what will happen from thermal radiation on fabric surfaces. So now you know you will have a heat problem.
AC to weaponeer. How's the IFI coming along?
Weaponeer to aircraft commander. IFI proceeding satisfactorily.
As you carefully check off each item of the in-flight insertion, Captain, you can tell that the preparation of the King weapon is moving along on schedule. But not too long ago, this weapon did not exist. To get King ready for Ivy, the weapon was being worked on in the States almost up to the last minute. So the weapon, minus the nuclear component, was ferried out to Quaj by a C-124. In the meantime, after the Mike shot, the Curtis sailed to Kwajalein. Assembly people from this ship work in conjunction with Sandia in preparing King for the airdrop. Following normal safety measures, the nuclear components of King arrived from the States in a separate aircraft. And now this super-efficient weapon, completed, ready, is taken from its shipborne assembly shop and moved under the cavernous belly of the waiting B-36. As the B-36 moves on its way to the target, the weather situation suddenly changes and becomes unsuitable for the test. And this means that the finely coordinated effort has to be canceled and the drop plane recalled to Quaj. For 72 hours, the King phase of Operation Ivy waits on weather. Men and machines who have been geared for the mission have to start all over again. Finally, shortly after dawn on November 16th, the go-ahead is given. This time there will be no turning back. This time, King is on its way to the proof test for which it was created.
Weaponeer to aircraft commander. IFI completed.
AC to engineer. Set climb power.
And so the King bomber climbs into the thin air of the stratosphere and levels off at 40,000 feet, its bombing altitude. Here the radar operator, or bombardier if you will, guides the aircraft to that four-dimensional yet imaginary spot so necessary for pinpoint accuracy.
Radar to AC, approaching target area.
The radar operator positions the aircraft in space with a movement of his hand, continuously running a cross-check between the radar bomb site and the visual system, back and forth, first peering into one scope and then into the other. During these critical moments, the vital facts flit across his mind. Ground zero, 1,900 feet to the north of Runnet on the Coral Shelf. Height of burst, 1,500 feet. Allowable margin of error from ground zero, less than 500 feet. Zero. In the 56 seconds it takes the bomb to fall, the men of Operation Ivy wait on Parry and Eniwetok Islands. Unlike the Mike phase of the operation, the King phase will be observed from land. The bomb is now at 8,500 feet, at 6,500 feet, at 4,500 feet, at 2,500 feet, approaching 1,500 feet. Watch the air overrun it. what about Mike? Let us now go back and examine the evidence and point up the statistical highlights of that device. Remember those final last seconds?
5, 4, 3, 2, 1, T0.
This is the largest fireball ever produced. At its maximum, it measures about 3 1/4 miles in diameter. Compared to the skyline of New York, this means that with the Empire State Building as 0 point, the Mike fireball would extend downtown to Washington Square and uptown to Central Park. In other words, the fireball alone would engulf about 1/4 of the island of Manhattan. The tremendous upsurge of air from the detonation rapidly pushes up the Mike cloud. Again, nothing of this height and width has ever before been witnessed. If the picture is stopped at this point in the cloud's growth, the height of the cloud is approximately 40,000 feet. This means that 32 Empire State Buildings at 1,250 feet per building could be piled one on top the other before they would attain the cloud's height at this time, roughly 2 minutes after 0. Some 10 minutes later, the cloud approaches its maximum. At this time, the mushroom portion of the cloud has pushed up to around 10 miles and spreads out along the base of the stratosphere to a width of about 100 miles, while the stem itself is pushed upward deep into the stratosphere to a height of about 25 miles. Later figures put the Mike yield at around 10 megatons or 10,000 kilotons. This means there was more energy released in this one shot, roughly 10 times more than in all previous atomic blasts combined, including probably those of Russian origin. Or to put it another way, 4 times more power in this one shot than from all the high explosives dropped by the entire Anglo-American Air Force on Germany and the occupied countries during the last war. The results of this tremendous power can be shown at the atoll. Here is an aerial photo of the test area of the atoll before the blast. And here is the same area after the blast, showing the crater caused by Mike. The outlined island in the center is former Illugelab, the 0 island. Sections of the islands on either side have been chopped off. The crater is roughly a mile in diameter. When it is illustrated that some 14 Pentagon buildings could be comfortably accommodated in this hole, the size of the Mike crater becomes more real. In profile, the crater gradually slopes down to a maximum depth of some 175 feet, or equivalent to the height of a 17-story building. The lateral destructive effects are the greatest yet observed from a single explosive device. Without getting into the areas of target evaluation or secondary effects, it can be safely assumed that there was complete annihilation within a radius of 3 miles, or out to and including all of Enjabie, that there was severe to moderate damage out to 7 miles or down to Ruggiero, and that light damage extended as far as 10 miles or down to Runnock. Relating this area of damage to a city like Washington, D.C. would present a picture something like this. With the capital as 0 point, there would be complete annihilation west to Arlington Cemetery, east to the Anacostia River, north to the Soldiers' Home, and south to Bowling Field. Complete annihilation, and that is mentioning merely the primary damage.
Well, it's all over. Mike shot and King shot are history, and we're back here at Perry Island winding things up. It's been a pleasure to help bring you the story of Operation Island, the work of Task Force 132. Now that it's all over, I have sort of an inadequate feeling. There's so much more that could have been said. But then in a presentation of this kind, one can only hope to give the broad brushstroke. And the men who told you the story, we're only able to pick out a few of the many. You get a feeling, even now, that nothing is really over. That this is a breathing spell, like a lull in battle before the next attack. The feeling is on this island, with the men here.
Yes, the coral sands of Eniwetok Atoll have viewed events in the fall of 1952, which less than a year and a half before would have been colossal accomplishments. Today, they are calmly accepted. This is characteristic of the progress being made in the weapons development program. What is new today is old hat tomorrow. And of the day after tomorrow, who knows what these Pacific sands may see?